Welcome to the second part of the virtual course number 7 dedicated to the ex situ analysis. In this part of the course, we will deal with X-rays and then follow to X-ray diffraction and X-ray fluorescence. So we should first start by seeing the range of the electromagnetic spectrum. We are of course used to some parts of this electromagnetic spectrum, namely the visible wavelength region. But of course, many other wavelengths are available, and the higher the wavelength that we are using, the higher the size of the object that will interfere. If we have lower wavelengths, we can go to smaller sizes. And when we are speaking about X-rays, the range of the wavelength is around a few angstroms. And this is the wavelength that is particularly important to study structures, since it is in the range of the distance between atoms in chemical bonding. In every techniques, we usually need an emitter and the receiver, and in the middle we will put an object that we want to study. So in this case we will need a source for X-rays, and we will need a detector of the interference that these X-rays produce with the object. The most classical way to produce X-rays is by using in the laboratory an X-ray tube. Here we have usually a filament, and these filaments will produce electrons that are accelerated into a target. The target is usually made of copper, but other elements can also be used, such as nickel or silver or rhodium, depending on the applications that we want. When these electrons reach the target, they produce two types of X-rays due to their interaction with this material. They produce the characteristic radiation that results from the excitation of the element of the target, and then the subsequent relaxation through the emission of energy through X-rays that are characteristic of the element of that target. And we have the continuous radiation X-rays due to the deceleration of the electrons when they reach the target. In any case, these X-rays produced by the X-ray tube are called the primary X-rays because it is the first time they are produced. We can then use the X-rays produced by this X-ray tube to study and analyze materials. Another way to produce X-rays is using synchrotrons. In this case, the electrons are accelerated first by a linear accelerator and then by a cyclotron, being injected into what we call storage rings. In these storage rings, they are made to follow circular trajectories, and through the insertion devices located in certain points of this storage ring, the electrons traveling at relativistic speeds emit collimated X-rays of high brilliance when they change direction. Then, using monochromators, we can choose the energy that we can work with. It is very useful for different types of techniques that use X-rays. It can be used by X-ray fluorescence, X-ray diffraction, but also to study materials using X-ray absorption spectroscopies. In any case, the X-ray spectrum produced by an X-ray tube, which is the most common application, is that we have at the same time white radiation, what's called the continuous radiation, and the characteristic radiation of the material composing the target. Usually, we have filters that remove the unwanted energies, and we remain with the K-alpha radiation, which is more intense and which is used for the different X-ray techniques. Maybe we start with X-ray fluorescence. X-ray fluorescence is used mainly for chemical characterization of samples. So we can determine chemical elements that are present in materials. The results can be qualitative, semi-quantitative, and quantitative. What happens is that we have sometimes certain limitations due to the equipment used, and usually lighter elements are more difficult to determine, usually elements lower than oxygen. What we produce in this technique is that the X-rays coming from the X-ray tube or from a synchrotron, they excite the elements existing in the sample. These elements that are excited will then return to the fundamental state, releasing energy. And this energy is released, among others, by X-rays, characteristic of the elements that are existing in the sample. So this is the secondary radiation or fluorescence radiation. We now have to have the means to detect this radiation that is coming from the sample, and that results from the interaction of X-rays and the elements in the sample. We have two measurement nodes. We can have an energy dispersive system or a wavelength dispersive system. If we are using energy dispersive spectrometers, we usually have solid-state detectors that have a high resolution. And through multi-channel analyzers, we detect all the incoming energies from the sample at the same time. We then can calculate areas below these peaks. And in this way, by comparison with standards, we can quantify the elements present in the sample. So for a given energy, we have a given element, chemical element. The other modes of detection is by using a wavelength dispersive system. In this case, through a set of analyzing crystals, we can discriminate between the different wavelengths coming from the sample. And different elements are attributed in 2 theta values. For this type of detection, we have to have high sensitivity detectors. The quantification of the elements is done by calculating the height of the peak, which is then compared with standards, and so an accurate quantification of the chemical elements in the sample can be given. The chemical analysis is dependent, of course, the quality of it, on sample preparation. But sample preparation can be minimum if it is already on the appropriate form. And so this technique can be considered as non-destructive in terms of recuperation of the sample or other measurements using other techniques. If it is a powder, the sample is already in its optimal form and can be used as it is. The same if you want a bulk concentration. And so also minimum preparation of the sample is necessary. Sample types can be varied. Then can be powders or bulk samples or pellets or beads or liquids. Of course, however, depending on the required quality of the results, if we want to determine major, minor, and even trace elements, we have to press these powders, producing pellets, or maybe even producing a glass and breaking down the crystalline structure existing inside the materials. This technique is not dependent in itself on the crystallinity of the materials, and many types of materials can be analyzed. But here we are more interested in the cultural heritage materials. So, different types and different origins of materials can be studied, such as stones, mortars, ceramics, pigments, glasses, and glazes, coming from cultural heritage objects, assets, or monuments. As a first example, we are going to see the type of results obtained for a ceramic statue of Saint Mary Magdalene from the 18th century that is at the Archaeological Museum of Carmo in Lisbon, Portugal, where the ceramic material was studied as a first step during conservation works. The piece has now been restored and is displayed at the museum. So the type of results can be seen where from the obtained spectra, using a wavelength dispersive system and with a set of standards for quantification, the chemical composition was determined, being possible to infer the concentration of the different elements, here expressed in terms of oxides. The major components being silicon, aluminum, and calcium, with some iron, as expected for this typology of materials. These results were then used to compare with other examples from the museum for datation and type of materials used during its manufacture. From the case studies of the HERACLES project, we can see here the resulting analysis from the Palazzo dei Consoli in Gubbio and the Gubbio town wall. Mortars from these monuments have been studied, and their chemical composition allows for an evaluation of the concentration of the different elements identified. These results were the object of a publication in the journal Heritage, and the correlation could be found between the different types of mortars that were recovered from these monuments. And the other technique that we are going to refer in this virtual course is X-ray diffraction. X-ray diffraction uses again the primary radiation of an X-ray tube. And by studying the diffraction of the X-rays from the incoming X-ray tube, we can analyze the crystalline structure of the materials. The equipment to use is very simple in its design. It just has to observe the Bragg's equation for diffraction, where there is a relationship between the incoming and diffracted X-ray beams, depending on the distance between crystallographic planes in the structure of the material. So here, no secondary radiation is produced, or more correctly, we are just interested in seeing how this Bragg equation is used. The examples and different case studies shown here were the identification of the structure for naturally occurring nanophases of ferrihydrite, a nanocrystalline phase that occurs naturally, was possible through the use of X-ray diffraction. In this case, and not as in the case of X-ray fluorescence, a set of peaks is related to one single crystalline structure. In X-ray fluorescence, each peak corresponds to a given element. In X-ray diffraction, a set of X-ray lines are coming from the same structure. So X-ray diffraction is used to identify crystalline structures. As can be seen here, for instance, in the case of ceramics, where there is a precipitation of crystalline structures inside an amorphous glass. Even when we are studying amorphous structures, some information can be gathered, as it happens here, where we mix different compositions of glasses and where we can see two amorphous bands forming, indicating the formation of two different glasses in the mixture. In cultural heritage studies, for example, it was possible during the compatibility studies between original materials and new products used in conservation works relating to glazed tiles from the 17th century in Portugal, the comparison between a commercial product for restoration that was similar to present-day glazes produced in factories against the chemical and structural composition in ancient glazes from the 17th century. Also from the HERACLES case studies, and now going to the case studies in Crete, Greece, the identification of black rust from the Palace of Knossos gave the identification of gypsum and anhydrite, while the identification of white crusts from the Culus Prostrus gave an indication of the existence of halite, a salt. We will end here the second part of the virtual course number 7, and the third part of the virtual course number 7 will be dedicated to the in situ characterization techniques.